Hello and welcome to another video. In this video we're going to be working on closest prime numbers in range. And in this one you have two positive integers, left and right, and you want to find the two integers between them such that they're both primes and the difference between them is the smallest among all pairs of primes. Return the positive integer array. If there's multiple, return the smallest one. So first of all, let's just say we just have an array of a bunch of numbers and it's a sorted order, because that's basically what we're going to do. We can go through left and right and figure out if numbers are prime. So if we have an array of a bunch of numbers and they're all in sorted increasing order, so let's say we have 4, 8, whatever, and so on, right? Or I guess it's not sorted. 14, 34, and so on. So yeah, let's just leave it here. So the smallest difference is always going to be between adjacent numbers, right? If I compare this number, I'm just going to compare it to the ones next to it, because that's going to be the smallest. I'm never going to compare these two. So that's kind of the same idea we can have here. Is once we figure out what numbers are prime, we can just check all pairs and which one is the smallest. But now how do we figure out if the numbers are prime? So there's kind of two ways to figure out if numbers are prime. One is we can check one number at a time, and to do that, you have to iterate through all of the factors of a number. So it's going to be up to the square root of the number. You have to check all of it. So this will be time complexity of n square root of n. And the reason we have to check for up to only square root instead of, I don't know why this is like this or this. Yeah, I don't know why this is so small. Interesting. Okay, I think I have to make it bigger. Okay, there we go. So the reason we have to check up to the square root instead of the whole number, we can basically get rid of all this now. We don't really need it. So because if a number has two factors, let's say we have a number n and it has multiple factors. So if it has two factors, one of the factors, you can have two cases. You can either have n is a perfect square, which is x by x, or it's going to be a number that's less than half of n, or the square root of n actually, right? So it'll be a times b, and one of the factors has to be less than the square root of n, the other one has to be bigger. And it makes sense why, right? Because if this is true, if I increase the left number, then the right number has to decrease, right? If a is bigger than x, then b has to be smaller. So if n has two factors and it's not a prime number, one of those factors has to be less than the square root of n, or it can be a square. So that's why when we check for if a number is prime, we just have to only go through the digits of 1 through the square root of n. And that would be n square root of n. And actually this problem, I think, had, I think it was 10 to the 6th or something, was the numbers you can have. So that would give you 10 to the 6th times 10 cubed, which is too slow. The other way to do it is, I think it's called the sieve of Aristophanes, or I never get it right. And that one is time complexity of, I think it's O(n) log squared n. So that one's faster, and it's good when you want to check if you have a full range of numbers. If I have number 1 through a million, if I want to check if all those are prime, then this is going to be the way to go. If I have a bunch of distinct numbers, then I can just check individuals, but here we actually have a range. So we want to check left to right, but actually we can just check 1 to the right. So let's say we have some left and right. Let's say this is 2 and right is 10. So the way this works is, let's say these are our numbers actually. So yeah, so let's say we have 0, 1, so on. The way this works is we also have to check only up to the square root of the top number, because kind of the same thing, where if a number has factors, one of the factors is going to be less than the square root of a number. So we actually only have to check up until the square root of 10, which is 3, and we can round up, so maybe we have to check these. So the way this works is, first we mark them all as prime, or we mark them all as, let's see, I think we mark them all as prime. Yeah, we mark them all as prime. So all of these are going to be marked prime. Then we know that 0 and 1 are not prime for sure, so we'll just say maybe green is not prime or something. So we'll say this is not prime, this is not prime, something like that. Okay. So yeah. Then we start at the next number and we'll go from 2 to 4. So basically what we say is, if the number is prime, then we're going to go through all of its factors up until the square root of n, and then we're going to mark them as, actually, to the square root of n, or no, we actually have to go through all the factors up until n and mark them all as prime or not prime. So here we're going to say like, okay, 2 is prime. That means we have to go through all of its factors up until n. So if 2 is prime, that means 4 can't be prime. So we're going to say 4 is not prime. And then we're going to go to the next one, right? We're just going to keep adding 2. So 6 and 8. So these can't be prime. Then we're going to go to 3. So 3 is not prime. So we're going to go through all those factors. So 3 is prime. So 6 can't be prime. It's already not prime. And 9 can't be prime. And then the last one is 4. So 4 is already not prime. So that means all factors of 4 will already not be prime because something else marked those. And you can see that's the case here. So we don't need to worry about it. So essentially the formula or the algorithm is make an array 0 through n, mark everything prime. And the other thing is, I forgot, the other thing is when we go through the factors of a number, we can start at that number times itself. We don't have to go through numbers like that number plus 2 or that number plus 3 or something, because those numbers will already be marked beforehand. So like when we check for 3, we don't actually have to check 6. We just have to check that number times itself, because anything less will already be marked prime. Because any factor of 3 that's less than 3 will already be marked by something else, right? Because this is 3 times 2. So that means if 2 was prime, it would have already been marked. So for 3, we would actually just check 9. So mark everything prime, then we just loop through numbers, up until square root of n. And then if it's prime, we start at that number squared and mark all factors as not prime. And then at the end, we'll just have this array of like prime, not prime, prime, not prime, and whatever. So then once we do this, we can just go through all our numbers again, and we can just keep checking, like, is this number prime, is this number not prime, and so on. And then all we have to do is just remember the last 2 numbers and then compare those. So like, so these 2 are actually not prime. So we'll check like this number and this number. These are 1 apart. So we'll say like our best result is 2 and 3. And then when we go to this number, we'll say like, what was the one before this one? It was 3. So is 3 and 5 better than 2 and 3? No. Now we're on 7. What was the last number? 5. Is this better? No. So we'll just return 2 and 3. And if we never got the 2 prime numbers, then we'll return the -1, -1. So essentially, we're going to build this. We're going to use this sieve to get the primes really quickly, and then from there, we just compare the 2 adjacent numbers in a linear scan. All right. So, and I think this is worth memorizing, the sieve and how to get the prime of just one number. Those 2 math things are worth memorizing, in my opinion, or like learning and figuring out how they work. Right, so let's say nums is 0 times right plus 1. Okay, and not 0. We're going to mark them all as prime. So we'll say true is prime. We'll say nums 0 and nums 1 are not prime, because 0 and 1 are not prime. Then we're going to loop from 2 to square root of right plus 1. This actually should be the ceiling, because this will be a decimal, so we can round up. Okay, I think floor will also work, but yeah, just in case. So we're going to say if nums I is prime, then we need to loop through all factors starting with I squared. We don't need to do I times any number less, because those will already be covered by a smaller number. So we can just say for, yeah, I guess we don't need this technically. So for j in range, so this is going to be I times I, right plus 1, and we're going to keep increasing by I. Nums j equals false, so it won't be prime because it's a factor of something. Right, so now we have this array. So this array is just going to, for every single number, is going to mark true or false. Now we just need to loop through left and right and get the best result. So we're going to say result equals, we'll just make the numbers really big just so the difference is really big. So we'll say the left is this and the right is this. And we're going to keep track of the last number, and we'll store this as like none. Last number that we've seen so far. Because we might have prime numbers and a bunch of like non-prime numbers, a bunch of composite numbers, so we need to store this. So we're going to say for I in range, left, right, plus 1. So if the number is prime, is true, I guess we can just do this. So if it's true, then this is prime, and we need to check. First of all, we need to check if the last number is valid. So if last number, then we can check if this is better. So if nums is true, and we have a last number, and these two, this difference, so nums I minus, yeah, I think it's the difference of the primes, right? Let's check if it's the difference or the difference in indices. Let's see. Yeah. Actually, sorry. So nums, so actually I is the number. So we don't need nums I, because nums, like this is all the numbers. So we can actually say this, if this is fine, but basically, so we don't need nums I, we just need I minus last number is less than result 1 minus result 0. So if this is less, then we're going to replace this. So we're going to say result equals last number and I. And then we're going to update last number to this current one. So last number equals I. Then we'll just return result if result 0 does not equal infinity, or negative infinity. Otherwise, we'll return the negative 1, 1 thing. Let's see if I screwed anything up. No? Okay. So there is another way to do this in some weird math way where they, and this is in the editorial, where like two prime numbers that are bigger than some difference apart are always close to each other. But that's not a realistic solution, and that's not something you're going to be expected to know, because that's just like a concrete math thing that you can know for this one problem. So I'm not going to go into that one. I think this is the more expected solution. And then, yeah, if you do the prime of every number, you'll get a TLE. So I think you just have to do this. So hopefully this is helpful. And yeah, this does come up in decent amount of problems, and it's good whenever you want to check in a range of prime numbers, or in a range of numbers which ones are prime. This is better than just doing one at a time. So this is like log squared of n, I think. Right, sorry, n log n squared of n. And then space. So for every number we do have this thing, right? So it'll be like O of n. Yeah. So yeah, kind of interesting problem. Hopefully it makes sense. Let me know if you have any questions, and thanks for watching.